Momentum Momentum impulse, work energy. Today we are going to discuss. In the dynamics, basically, we have considered two things. One is the Newton's law, D'Alembert's principle, in addition to the kinematic analysis for different types of motions. That is the translation, rotation, and plane motion. Okay. So now, today let us see. We are going to discuss basically the principle of impulse, momentum, and energy methods. So many energy methods are there, like Lagrangian method, in addition to Rayleigh method, Rayleigh-Ridge method, Galerkin method, like that weighted residual methods, etc. are there, but those we are using in advanced courses like finite element method, computation, fluid dynamics. But here we try to discuss with reference to the basic systems like particle and rigid body, how these systems are considered, energy methods, the principle of virtual work, etc. We are going to consider impulse and momentum energy formulations, and the extension impulse momentum extension is collisions. In impulse momentum, we will consider linear momentum and angular momentum also. Okay, so these are the things which we are going to cover today for both the civil engineering as well as the mechanical engineering. That means basically today we are going to concentrate impulse momentum, energy methods in both the cases, mechanical also, impulse momentum, linear and angular momentum, and energy formulations, and little bit collisions also. Okay, so these are the two topics we are going to cover in the today class. The momentum impulse, work energy, what are the learning outcomes generally we try to represent. We have to represent or express dynamics of a particle at rigid body, and we already differentiated between kinematics, kinetic, that we have to keep in mind when we are solving any other methods. You apply the concept of different dynamic principle, Newton's law, dynamic D'Alembert's principle, momentum impulse, work energy. These four ways any dynamic system is considered, or you can modify later other methods also, like Hamilton principles, Rayleigh method, Rayleigh-Ridge method, weighted residual method. There are so many other methods are there for statics as well as dynamics. See now, today the main learning outcome is derive an expression for representing moment impulse equation, work energy. That means the same dynamic problem can be solved by using two more principles. That is a modification of Newton's laws basically. Moment impulse equation, work energy equation are basically a modification of Newton's laws. We have to represent the kinetic equation for translation, rotation, and plane motion of particle and rigid body. The concepts must and should be, you have to understand every student, then because if you want to deal with the physical systems, which is more complicated and cumbersome, it consists of number of loads, the system is complex nature, lot of complexities are involved. To solve such a problem, you should have fundamentals to be understand very without any ambiguity, and update your knowledge by other methods, by other applications, etc. These are the learning outcomes what we are going to, every student will get today from the today class. So now let us see, the kinetics already defined, it is again a kinetics, is the relations between the force acting and the cause of the motion. That is, force means it is a force system required to produce a given motion. This cause of motion can be represented today moment equation, moment impulse equation and work energy. Moment impulse and work energy, which is the analysis type of force causing the motion. Type of force causing the motion. The dynamics is the study of the force as it works on rigid body in motion. Dynamic conditions are today what we are going to discuss, these two concepts for translation body, rotation body and plane motion. Okay, so this is how generally we will consider the system. How we will consider the dynamics with reference to translation, rotation and plane motion. Okay, so these are the main areas which we are going to touch in the today class. There is a 9th class for the gate. But here before I am going into the actual subject, my dear students, the crux of engineering mechanics problem is there are a number of principles are available both in statics and dynamics. Based on the given data of the problem, whether I have to go with the Newton's second law of motion, F is equal to ma, or whether I can solve with the D'Alembert's principle, both are almost same. One is you are keeping dynamic as it is and another is converting dynamic problem into static problem that we are calling as a dynamic equilibrium. Then moment impulse equation, then work energy equation. Okay. So these are the things what we are going to discuss. From your point of view, please carefully observe in what conditions we are going with F is equal to ma. In what conditions we will solve the problem moment impulse, and what are the other conditions we are going to solve work energy principles. See, this part you have to carefully observe when we are discussing moment impulse work energy. Compare with Newton's law and D'Alembert's principle also. When we will use that equations and when we will use these equations, because finally it will yield the same result. The type of because of force, what is the cause of the motion, we have to decide. Whether you can use the Newton's law or a D'Alembert's principle or moment impulse or work energy. See, here crux of the problem, dynamics people are saying difficult. It is not difficult. What principle we are going to apply, if you have a clarity in that, it is very, very easy subject. Why? Because once you represent a free body diagram, you resolve the force in x direction, resolve the force in y direction, solve the equation, get the solution. That's all. If it is a D'Alembert's principle or Newton's laws. Similarly, vice versa in case of moment impulse work energy equation. So that's why please be careful when we are discussing these two concepts. You have to compare with the earlier what we have done. The prerequisite knowledge is always when we are discussing in this class what we have done in the previous classes, you have to recollect and compare with your mind when we are discussing a particular point. That's one thing, my dear student. For a gate point of view, you need an overall view of all principles. Then you can easily attack this problem can be applied which method, in what conditions. Okay, now let us start with the linear motion and the rotational motion. This slide I have shown yesterday also. But please simple recollect the things, 2-3 slides I am repeating every day. Newton's second law, F is equal to ma, linear motion, that is a translation. Here, this is Newton's second law and this is Newton's second law. Both are Newton's laws only. But only thing is, this is for translation and this is for rotation. For a plane motion, you combine both. In translation, rectilinear translation, curvilinear translation. That's why rectilinear and rotation, if you can combine, we have 2 degrees of freedom, 1 and 1. If you can combine curvilinear and rotation, we have 3 degrees of freedom, 2 translations and 1 rotation. Okay, this is how generally we will consider. Then momentum. Momentum is equal to mass into velocity, because Newton's second law also can be represented as the rate of change of momentum. That means This you can write as dv by dt, acceleration A is equal to dv by dt. If mass is constant, d by dt you can take outside, then mdv. Okay, that you differentiate or integrate both sides. The integral dv is left over, the integral differential will be cancelled. This is mv. This dt you move other side. This is integral 0 to t ft. That is what the impulse momentum. Today what we are going to discuss. But here this rate of change of momentum is called, that is d by dt of mv is called a momentum. That f is same, now we are calling the p to differentiate force and momentum. Mass into velocity, kg meter per second. Rate of change with respect to time. Whereas angular momentum, that is the rotational case, degree of freedom, the momentum is angular momentum. It is a linear momentum and it is an angular momentum. Mass is replaced by mass moment of inertia. Linear velocity replaced by angular velocity. This is the difference we are going to derive today. Work done is the force into displacement, linear displacement, x, translation x, the integral. Whereas here work done is, instead of force, we have to use the torque or a moment, that is t or a moment, and dx replaced by d theta because it is rotation. If it is a plane motion, combine both the equations. Okay. The kinetic energy is half mv square. Kinetic energy is half mv square, and this is half I omega square. Mass into velocity square and mass moment of inertia angular velocity square. Power is equal to F into V and T into omega. Torque into omega. Force into velocity and torque into omega. P is equal to T omega. Force is equal to F into velocity. See, this is how the systems comparison between the translation degree of freedom and rotational degree. Mass moment of inertia, you know very well, we will discuss at the later stage, but how to calculate. But at this stage, what is the mass moment of inertia? Mostly considering a parallel force system here. And you have to derive time pyramids. We will take one class on that, how to calculate this mass moment of inertia. Okay. The I is equal to mr square, or for a shell, thin cylindrical shell, solid cylinder 1 by 2 mr square, sphere 2 by 5 mr square, and thin rod 1 by 12 mr square with respect to center and axis, with respect to left hand or right hand, then use a parallax theorem. See, like that you have to calculate what is the mass moment of inertia. See, now that is what is the little bit repetition of yesterday class. Now let us start with the general dynamic equation of motion by using momentum impulse and work energy. Here, see what we are going to consider first, a translation. In that, the rectilinear is only 1 degree of freedom x or y, whereas curvilinear both x and y. And rotation and plane motion. See, this is how generally we will try to consider the system for translation degree of freedom, rotation degree of freedom, and the plane motion. Suppose this is a flywheel, the weight is falling. That means there is a shaft here, on the shaft flywheel is fixed, let us assume. This is not a prismatic, it is a non-prismatic cross section. For understand purpose, simply represented. Let us, this body is in rotation, this body in a translation. It is what is called the plane motion. Okay. This is the force, the weight, and the F is equal to ma. Here there is a pin joint, there are reactions. And rotation is I alpha mass. So this mass is considered this mass. This body is in a linear acceleration, this body is in angular acceleration. Now here, initially at rest, both. Now I am holding this weight and releasing my hand. Once you release the hand, this weight freely falling. With the thread is there, which is roped with the shaft. See, when it is relieving, the flywheel starts rotation. Okay? That means what is happening when it is the loss in potential energy is equal to gain in kinetic energy of the system. Or in other words, momentum. There is a momentum also, the transformation. These two are interrelated. See, now if we can consider such a system, I alpha, MA, upward reaction, downward reactions, if you can consider, then see that how the system can be represented. Okay. So now here definition is impulse is amount of change in the object's momentum. Just now I given a flywheel example. When the weight is falling, there is a momentum changes in the other body. Or mathematically represent impulse is a product of F into delta T. That is force into within a small duration of time. The heavy force is applied. That is what is the impact. Indirectly impact. A collision. When you are discussing a collision problems, within a small duration of time, the large force is applied. Suppose when the cricket ball is hitting a bat, within a small duration, the player will hit the ball with the bat. Because both are rigid here. Otherwise, a lot of deformations are taking place. The rigid body is an assumption here. Okay, is equal to the change in momentum. We'll consider the momentum example. Delta P is equal to mvf minus mvi. And whereas the force in a duration of small time. Here the displacement is dx, here the d theta, delta theta. Here velocity is v, the angular velocity, acceleration a, angular acceleration. The mass m in place of I, like a translation degree of freedom and rotation. There is a straight line motion. Inertia in x direction F, and it is a torque with respect to z axis. Newton's second law, F is resultant force is equal to m into A, these two, and I into alpha. T is equal to I alpha. Torque. Work is equal to force into displacement, torque into angular displacement. Kinetic energy, work and energy. Work is this. Energy is kinetic energy of m square. M is replaced by I. Linear velocity replaced by angular velocity, I omega square. Momentum P is equal to mv, final velocity minus initial velocity. P is equal to mv. The change in momentum is this. Final momentum minus initial. P is equal to mv. M is replaced by I. V is replaced by W. That is the linear and angular momentum. Impulse is F into delta T is equal to delta P. That is here the torque into delta T is equal to angular momentum. Or in other words, if you can compare the angular momentum for a degree of freedom in a rotation, this is a translation rotation compared pure rotation, the angular momentum is I omega and the kinetic energy is of I omega square, this one. This is the rotation. These two are translation. So this is how generally we'll try to represent the equation. We'll derive how you got this from the basic Newton's second law. First, let us understand the simple concepts. See, now these are some examples. So students, there is I think network problem once again. We stopped somewhere here where the body is having a rotation, that is the body and translation, rectilinear motion and rotation. This is I alpha, moment is equal to I alpha, force is equal to ma. Newton's second law and Newton's second law. Both are Newton's second laws. So now let us consider here impulse is nothing but as per Newton's second law, you know very well moment impulse equation. This is we have considered the translation part. This is the rotation part. Translation is force is equal to F into dt. How to obtain this relation is here. If you can consider sigma F equal to resultant force hello 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 sir, mouse button. Resultant force is equal to mass, that is W by G into acceleration. Okay, so this is equal to W by G. Let us say mass is constant. Mass is constant. Acceleration I am writing as dV by dt. So this is what we are representing. Now in this case, this dt, if the mass is constant here, then what we have to do is this you move the other side, otherwise if mass is constant, then d by dt of W by G into V. See, this is a modification of Newton's second law only. This is what we are calling the momentum, change in momentum. Okay, this is what is your MV concept, final velocity minus initial velocity. If you can consider, this is the rate of change of momentum, and this is the impulse. That's how we will try to represent the body and try to solve the problems. Okay, so we'll consider the problem with delta P is equal to FTT. Now this is what the angular momentum is. This is the angular momentum, the kinetic energy of I omega square and rotation when the body in a rotation. This is when the body in translation. Same thing when the body in a rotation. Because that's what today we are going to discuss momentum impulse and work energy principle. Now let us consider the one example where impulse and momentum is the vertical wall, and when it is impacting, the collision will take place. This is what is called the crash worthiness collision. We'll consider this as crash mechanics. This is generally we are using a high body, that is what is called the finite element methods and things we will use. And this is a linear momentum. Why? Because the body is moving in a translation, a linear translation. Okay. So now this is what practically the person is pulling is not a possible way as well the weight point of view, but some rare cases records people are Sigma Maragan. Now, dear student, there is a small internet problem here, power problems. Last night, power is not there, that's why it is giving power. But whatever it may be, let us start with this is where the change of momentum, when you are considering a linear momentum, the translation hitting a vertical wall. This is one best example. This is where the collision crash worthiness are taking place. Okay. Now, this is another example where the impulse, the body hitting or pulling. The two examples you can accidents as well as pulling. The momentum it takes place. Or in other case like boxing, initial moment and final moment. Here the important point is the force is equal to mass into acceleration. Mass can be represented dv by dt. This dt, if you move other side, f, this sigma f is f. This dt integrate both sides. F dt is equal to m dv, m delta v. This integrate, this dt can be represented from 0 to t, it is t. Force into time is equal to mass into velocity. Change in momentum. This force and time are inversely proportional. The inversely proportional force and time. That is how we will try to represent the system. Okay. Ft is equal to mv, mass into velocity. So this is how we will try to represent the system. impulse momentum equation. The conservation of momentum. The conservation of momentum is a cornerstone of that is where the two bodies are hitting. One transformation of momentum to other body. This is what is called the conservation momentum. That also we'll try to discuss, and collisions. These all are there in our syllabus. Conservation of momentum, when it is a collision, how it elastic impact or plastic impact, what is the crash worthiness? Because the deformations are taking place. It is not only the elastic, the plastic. We are assuming a rigid body, but this mechanics is again is different. Crash worthiness and other things. But little bit concept of what is the conservation of momentum, what is the type of collisions we have to understand. Again, similar case, both are similar. Earlier is pushing, now pulling. This is pushing, and now pulling. Suppose when you push with the same force for twice the time, you impart twice the impulse and produces twice the change in moment. Okay? When bat is hitting the ball, any sports, like a cricket, a heavy force is acting small duration of time. That is what is the impact. Large force, small duration of time. This is what the force, large force, small duration of time. That is what when a long tennis ball is hitting the bat, cricket ball is hitting the bat, when we are playing a football, when ball is hitting with your leg, when you are taking a volleyball, ball is hitting in your hand. All these examples will be considered as momentum or conservation of momentum principle. Just we want to conduct the momentum concepts here and try to solve the problem. Okay. And the momentum is the change in momentum. We'll consider the conservation of momentum, impulse momentum. Impulse momentum can be considered, the change in conservation of momentum concepts. Here before and after the collision takes place. See, before collision there is an impact. See here three problems. This is a stationary body, there is no momentum, crash is taking place. But when you are hitting, the momentum takes place, conservation of momentum. Okay? Well, the transformation is taking place. See, this is how generally we will consider. Due to this impact, there is a collision or maybe a crash. Collision is in the collision between the two bodies. After that, what is happening? The crash. Either this part is crash or the face. That's why we'll use the airbags to avoid such type of problem. Here there is nothing will be happened if the airbags are removed when the high collision taking place. Okay. Now see here, this is a rigid body, but there is a captured, this is a deformed body, like grass. When a vehicle is hitting the grass, nothing will happen because it is not rigid, not rigid. When it is hitting the vertical wall, the vehicle shape change. This is the difference between the momentum as well as the impulse and momentum. Or if we can take best example, it will bounce back, it will in the body itself. Here when you release the ball, like simple pendulum expression, there are a number of pendulums, one touching with the other. If you rise into some level and release your hand, then it will impact is taking place. Okay. So now this is what we'll consider the body, the transformation of momentum, or the potential energy lost by gain the kinetic energy. Both principles, the same concept. Momentum change, this is what is the conservation of momentum, and ball is hitting back the another ball, simple pendulum, spherical ball. It will transform from here to here, here to here, here to here, and here to here. See, like that, the transformation is taking place. Now, this is what is the impulse. Force within a small duration of time, 10 seconds. See, earthquake, best example. Within a small duration time, huge force is applying, lot of damage takes place, like cyclones, when crossing the lot of damage. So this is what the force direction, velocity direction, momentum direction, etc. Depend upon that, we can consider what is the momentum. F into delta T is equal to mass into dV. dV is nothing but final velocity minus initial velocity. See, this is what is called the impulse. This is an impulse, and this is the momentum expression. Or in other words, see, F is equal to ma. Acceleration is v minus u, final velocity minus initial velocity. Now, if we can see the summation of forces is equal to mass into dV by dt. This dV is v minus u. Okay, the change in velocity with respect to time, dV by dt, m into F is equal to mass into v minus u by t. The Ft, if you multiply, m into v minus u. And this is how we will consider the case that force, this is what is called impulse, and this is what is called the momentum. Okay. So this is how generally we will consider the body, the change in momentum. Now see the impulse, this reduce the average impact force and extend the collision. Okay, for a given change of momentum, conservation of momentum. For a conservative system, this effect is zero. There is no loss or there is no gain. That is what is called the conservation of momentum. See the same expression, F into T is called the momentum, mass into A, acceleration is dV by dt into T. M delta V, T will be cancelled. This is what is called the momentum, impulse, and this is the momentum. Okay. Now let us see that there is a vertical wall. The two bodies V1 and V initial and V final. This is the initial velocity and this is the final velocity. And this is the initial and this is the final. We have to consider. When the vehicle moving with velocity Va, a car rebounds and thus encounters a velocity change. If you can see 5 meters per second, a car rebounds and thus encounters a velocity of change 9 meters. Change in velocity means this minus this, it is opposite negative, minus of minus, 5 minus minus 4. It is what is called, there is 9 meters per second. In case B, it is very rigid ball and it is where it is not rebounding. Rebounding is characterized by large velocity. This one, large velocity. Okay, in case with the car does not rebound and does encounter the velocity change, 5 meters per second, only 5 meters change takes place. The loss by this body, gained by the other body. Okay, even it's a fixed case. So this is how the momentum can be explained. Or in other words, initial momentum ME1 and the force is applied on this resultant force on mass M. There is a force F2 or a resultant force F into dt is equal to the momentum this body due to the final momentum takes place M into V2. Or in other words, integral F dt is equal to M V2 if this can be moved into the other side. See, that is what is called MV1 and represent this. See, that is what is the expression of this case. Impulse is equal to final momentum minus the initial momentum. Okay, so this is what the initial momentum when is hitting the takes place. This is the case. When is leaving, this is the case. So this is how generally we will try to represent the body when we are taking the momentum. Okay, see here, this is what we are calling as the resultant force RDT. Initial momentum, final momentum, and force into within a small duration of time. See, the same thing, vector representation, because it's a vector quantity. Now if you can consider this vector is in this direction, this is the vector, and let us say the resultant force magnitude and direction, this is parallel to this. Then the final, the closing of the diagram is the final velocity. Okay, this is the initial and this is the final. See, MV2 here, MV2, impact force and moment. The same when two more particles like this, MV1 and MV2. Now the summation of, if it is a no external force, it is 0. See, then initial momentum is equal to the final momentum. That is what is the conserved. See, that principle is called the conservation of momentum. Initial momentum is equal to the final momentum. There is no loss or there is no gain in the system. See, that is what we are calling as the momentum, impulse momentum principles. See, now let us same concept when the ball is hitting when ball is freely falling, it will bounce back. Due to acceleration duty, it is falling. The potential energy gradually decreases, the kinetic energy will gain. Hello. చెప్పండి. వద్దాం ఎక్కడి నుంచి వద్దాం. So now what we have to do is, when the ball is freely falling, MV, and this is the weight of the ball moving upwards. After the momentum transfer takes place, it is going up, MV2. Okay. So this is what is the impulse force. When it is hitting, the force is because of the surface is bounced back, and this is what is the bouncing back. So now what we have to do is, here if you can see this example, 300 newtons, initial momentum, it is at rest, it is he is applying velocity, 600, that is the final, this is the final momentum, the initial at rest. velocity is 4 meter per second is applying. Now final momentum minus initial momentum, final momentum this, initial momentum is 0, no initial velocity is equal to, this is what the momentum we can use, P2 minus P. This is dp part. Okay, so like that we can transform the system. These are the examples which we explained simple. Now let us consider what is the conservation of momentum in translation or a rotation. Now this is what the body moves along a straight line. It is having a velocity v1, it is having velocity v2, both are moving opposite. The initial momentum mv1 plus or minus mv2 depend upon velocity is given, these are the direction. Forces are opposite. This is also practically the velocity is in this direction, but that is the deriving the expression I am using this sign convention. If it is moving opposite, you have to put a negative. Otherwise, you have to put a positive. Okay. mv1 plus mv2 is equal to m1 u1 plus m2 u2. So this is how generally we will consider the system. mv1 is equal to mv2. This is what is the body in a translation. mv rotation, this is already a number of times explained, but only body is in translation, body is in a rotation. Okay, net moment is nothing but rate of change of the momentum. You can consider I omega, final angular velocity I omega. This is the conservation of momentum for translation body, this is the conservation of momentum for rotational body. The final momentum minus the initial momentum. Okay, so this is how generally we will consider the case. Now let us see a smooth balls to approach each other. Approach each other is u1 greater than u2. Both are moving in the same direction, but one approaching, this approaching this, moving along a CD, line CD. In the absence of external impulsive force, let the velocities of A and B just before the collision be u1, u2. After the collision be v1, v2. Because this ball is heavier when it is hitting, compare with this, this is less, obviously. Now the momentum is equal to m1 u1 plus m2 u2. Then together it is moving. M plus m1 plus m2 is the constant. If velocities are different during impact, this is the equation. After impact, this is the equation. At the time of impact, there is a common velocity within a small duration of time. Okay, so that is how we are using m1 v1 plus m2 v2. This velocity is m1 u1 plus m2 u2 by m1 plus m2. This velocity is m1 v1 plus m2 u2 plus m1 plus m2. Now this is how the expressions can be represented. Change in momentum is equal to of any one body during deformation. m2 is equal to v minus u2 during deformation. During deformation, there is one more common velocity v. u2 minus v for m2. For m1, v minus, that is u minus u1 minus v. Okay. This is what is the impulse of deformation. This is what we are calling the coefficient of restitution. You can obtain the ratio. This coefficient of restitution depends upon the elastic impact, plastic impact, this may vary. Now let us see, this is what is the coefficient of mv2 minus v, v minus v1, change in momentum during deformation, this part. Okay. before, this is before, and this is after. Okay, that ratio V2 minus V divided by V minus U2, final minus initial. Initially this, with reference to a particular body, with reference to M2. M2 is V2 minus V, same M2 V minus U2, V minus U2. That is impulse of deformation, impulse of after for a particular body. If you can write, this is one equation. Okay, that you substitute, then we got common velocity V is equal to, this common velocity is equal to M1, this V after small duration. Okay, that we can substitute here, these two cases with final velocities, and with, then we simplify. This is what is the coefficient of restitution. This is one parameter is very important in collisions. E is equal to 1, some cases like elastic plastic cases, semi-elastic, semi-plastic cases. Generally semi-plastic only considered. Elastic only will consider one elastic nature. Plastic or fully plastic, because the point why we are in elastic is, if you know the load, it regain its original shape. This E is called the coefficient of restitution. Momentum, why we will bother about momentum is, you have already learned the kinetic energy combined with the gravitational potential energy can help to solve many problems when the body in a motion. Another important concept is the collision. Why the collisions takes place. On the camera, it is very important to be able to find out, figure out what's going to happen when the object is collapsed. And simply energy methods usually, it is very important to be able to figure out what's going to happen when the object is collided, like a collision, crash is taking place, crash worthiness, so elastic and plastic. Simple energy method don't work in collisions case. So now this is what is the angular momentum in a rotation part, how the conservation of momentum. Momentum is equal to I omega, I into omega, angular velocity. If you differentiate dl by dt, this is d by dt of L I omega, I into d omega by dt. dl by dt is equal to d omega by dt is alpha, I alpha. Since there is no external torque, when there is no torque, this term is 0, the torque. Obviously, the momentum is conserved, that is I alpha. Hence, I omega, d by dt, when you write I omega is equal to L. L is I, this is L. L is constant. The initial momentum is equal to the final momentum. I1 omega 1, I2 omega 2, I1 omega 1, I2 omega 2. You have to figure out the things. The collisions are taking place. Now let us see this is a simple derivation given in the Timoshenko textbook. That book is very, very useful book from the gate examination point of view, because it will give concept very clearly. Very few number of problems will be solved, and it is using a scalar notation. But the concepts are very, very clear. But exercise problems are, most of the competitive examination, Timoshenko exercise problems are coming. There is a standard textbook in engineering mechanics and other also. But this is a scalar notation, the book. like Singer, Sames, Hebler, and other books there where there are the vector notation is following. The force x within a small duration of dt. Okay, this equation x is a large impact force during a small duration of time dt. This is how we'll consider momentum of a particle. W by g x double dot, because this is the Newton's second law, can be represented as the force is represented as x is equal to mass into acceleration. This acceleration is dv by dt, velocity with respect to time. That is nothing but v is dx by dt, d square x by dt square. That is what we are calling is x double dot. We can write like that also. When x double dot is dx dot by dt, that is dv by dt, nothing but v represented as x dot. W by g into dx dot by dt is equal to the force. Now this d by dt you take outside, mass into velocity. Mass into velocity x, d by dt of x. Then dt multiply both sides. The differential of mass into velocity x into dt. Okay, this is how we will try to represent the equations. And integrate both sides. When you are integrating, this and this will be cancelled, and the velocities you can make v1 to v2 or v final to v initial, v final and v initial velocity, v1, v2, and find out the momentum. Okay, so this is what is the meaning of a small large force. This is a force x or f. Large force is applying within a small duration of time. When you are playing a cricket, ball is hitting a bat, like that. Number of examples: earthquakes, cyclones, when it is crossing, high winds are coming within a small duration of time. When football ball is hitting with leg, volleyball when you are hitting with your, these all are impact forces, the best example. Okay, when enemy targeting your body, defense in the border, your body should be high resistance. Otherwise, the lot of impact force, the enemy's shells bombarding, bullets bombarding, etc. So these all will be coming as a momentum impulse equation. In that we will consider the conservation of momentum. Okay. See, this is what the day W by G x dot is equal to x dt. Now if you can integrate both sides, within a large force is applying a small duration of time. Now let us see here. When you are integrating left hand side, this is x dt, integrate both sides. When you are integrating, the differential integral will be cancelled, one constant is coming. This is the time, is the variable is time dt, you can vary from t1 to t2. Okay. So this is what the time t0 to t or t1 to t2. If it is starting from rest, it is 0 to t. If it is starting not from rest, initially not from the origin somewhere else, already is having some time t. So now let us see the boundary condition. When time t0, there is already some initial displacement, let us say, the initial velocity. Now substitute time t0, it is 0, x dot becomes x0 dot, then c is equal to minus of this, you move other side, that is c. That c you substitute here, that is final velocity minus initial. When the integral or definite integral, we need a boundary conditions. If we substitute the boundary conditions, w by g x dot minus w by g x0 dot. Okay, 0 to t x into dt. See, this is how generally we will consider the equations represents a differential equation of momentum of particle in time duration t. Then obtain the c you can substitute here. This is what is called the momentum. This is the impulse. This is a standard representation. This notation is following in Timchenko textbook, Timchenko Engineering Mechanics, Timchenko. But basically, if we can see here, one thing we have to understand, this equation is derived from the Newton's second law. This is where we have started. We have converted acceleration is equal to dv by dt. V I am representing as x dot, acceleration I am representing x double dot. V is dx by dt and acceleration is d square x by dt square. That's all. And that I am modifying like this. Then because it is constant, if we take a satellite, when it is reaching a particular level of orbit, the mass is changing. Okay. See, in that case, when the mass is changing here, when the mass is changing, this cannot apply, because this is only possible, this conversion, if it is a constant. If it is a variable, this is not correct. Okay, that's why you have to see that those assumptions. Now the change in velocity, final mass into velocity, initial velocity, change in velocity is equal to force into within a small duration of time t, 0 to t. That is what the expression dmvx. Let us assume that there is no force particle, there is no gain or loss in the system. Ideal system, if you can consider, during finite interval of time, is equal to the impulse force acting. That is equal and opposite impulse forces acting. Let us assume it will cancel with each other. Then it is 0 and momentum is conserved. dmv is equal to 0 means mv is constant. Initial momentum is equal when the weight 1 and weight 2, the of weight 712 newtons, indirectly around 71 kgs, means a man of weight 712 newtons stands in a boat so that he is 4 meters from a pier on the shore. This is the pier on the shore. From here to, he keeps walking towards shore. When he keeps walking, the tendency of the boat, this momentum, okay. Then when he is moving in this direction, the boat tends to move in the opposite direction. Then he walks 2.4 meters in the boat towards pier and then stops. He stopped. How far from the, because when he is moving 2.4 meters this side, it is also moving. That's why the way the distance is changing towards the pier and then stops. How far from the pier will be at the end of the time? The weight of the boat is also given 890 newtons, around 890 newtons. That is, boat weight is more than the human man weight. That is one example, one thing you have to, small variation is 70 to 1 point something, the 89 kgs or 712 newtons, 890 newtons. Let V naught is the initial velocity of man, time t. Okay, the velocities are not given here, if you can see, only the distance are given, both weights are given. Okay, this is the input data, both weights and the distance from here to here is 4 meters and here it is 2 point. And it is moving with a constant velocity. Okay. Impulse momentum is one more important point is if the acceleration data is not given, let us F is equal to ma or a D'Alembert's principle. Those principles are used when the acceleration is given. When the acceleration is not given, we want to discuss in terms of velocities, we have to go for momentum. Or if force is a function of time t inversely proportional, we'll go for impulse. Okay. See, that is one thing you have to observe. When the data is nothing is given related to acceleration, the first and foremost point is we cannot solve the problem with either Newton's law or D'Alembert's principle. Now, the other alternatives are momentum, impulse, work energy. Work energy is with always force will be there. If there is no force, no question of dynamics. In the conservation momentum, force is there, but net force is what we are in will cancel with each other. But that is again a further assumption. And we are making the momentum is conserved. The initial momentum, final momentum, etc. That is how the problem will be considered. Okay. The go towards the fire and how far from the fire will be at the end of the time. Weight of the boat is 890 newtons. This one, man weight is 712. Initial velocity of the man moving like this. The value is not given, but it is moving. This is the final, this is the velocity of a boat. Okay. So it is moving s is equal to ut plus of 8 square. A is constant here. Because conservation system, conserve means it is almost indirectly we can say that due to the nature it is moving. Uniform motion otherwise, V naught t into x. X is equal to Vt. Okay, the x is given, is moving 2.4 meters. This is a kinematic expression. Kinematic analysis I am doing. S is equal to Vt. V naught is in terms of t I represented 2.4 by t. That is one equation. Okay. So now the two bodies we can compare. Here only I have taken the man initial velocity time to reach 2.4 meters. I use the kinematic relation 2.4 and the value is known to me. Then the t is unknown, v naught is unknown. I represented in terms of one variable. V naught is equal to 2.4 by t. Okay. Let v the velocity of the boat towards right according to conservation of momentum. Boat is at rest initially. That velocity is 0 because see here the weight of a man is W1, the weight of the boat is W2. The initial velocity of the man is moving is some V0, but boat is at rest. Due to movement of this, it will gain some velocity. Okay, see that is what the expression common velocity it is moving. Together they are moving, not one. Boat is moving and man is also together moving. W1 common velocity. Initially boat is at rest. That's why that velocity is 0. Only the man is moving. That is the W1 into V0 plus W2 into let us say some V2. That V2 is 0 here. V1 is equal to V. V1 is equal to V0 and V2 is equal to 0. That's why the second term 0. From this V is equal to this. This V0 already we represented here. V0 is 2.40. That you can substitute here. V0. Okay. Then find out distance covered by boat is x is equal to final velocity into time. Okay. The time is already we got. V is already got. V into t. The t and t will be cancelled. V is this. Weight is 712. Distance is V0 is 2.4. This V0 is the previous equation. 2.4 by t. The 2.4 by t will be cancelled. Now this is the value 1.027. Out of 2.5 meter, it's 1.07 together is moving. The position is, that means the total. The boat is moving forward. This is the distance 4.5 plus s, total distance. In that, how much is the man movement? 2 point is going to see, s is the distance of the boat is moving in this direction. That is from here to here 4.5 plus how much is the s. From that you have to subtract, he is moving 2.4 meters. Okay. The boat movement is, this is the boat movement towards right side direction. That is s is equal to 1.067 meters. Position of a man from the fire 4.5 plus s minus x. Okay, this is how we can determine. Now let us consider another problem. Two blocks are W1 and W2. One is at rest. Note down. An automotive weight 534 kilonewton has a velocity V1 of U1 of 6 kilometers per hour. 6 kilometers per hour. And blocks into a freight car of weight 86 kilonewton. There is one car hitting the another car. Automotive weight of 534 newtons, heavy vehicle hitting the small car, freight car of weight 86 kilonewtons. That's at rest on a track. After coupling of what velocity v, there is a common velocity together, the entire system continues to move, neglect the friction. Because here we are using a conservative system where there is no loss, there is no gain. That's why the friction is obviously zero. When we are applying a conservation of momentum means, by default it is a friction zero. That is an assumption, because there is no loss and gain in the system. So now the W1, V1, W2, V2 initial at rest, W1, U1, W2, U2, after hitting, they move together as a single, because this is a small weight and this is a heavy weight. Obviously both are together moving with a common velocity. If there is an impact, maximum force is up, sometimes may not be moving a common, but here impact force is zero. That's why we can assume that moving at a constant velocity. W1, U1. U1 is given 16 kilometers per hour, converted into meters per second, that's 5 by 18. Multiply W1, U1. Both are given. This is W1, this is U1. W2 is this, U2 is 0. Why? Because it is at rest. After hitting, both are together moving. That is W1, W2 into velocity V, common velocity. That can be determined by moving this term this side and simplify, we'll get. See, like this we can use the principle of conservation of momentum. Okay. Now note down another problem. Is 67.5 weight man sits in a 333.75 newtons canoe and fire a bullet and fire a rifle, otherwise fire a rifle, and the bullet coming from rifle is moving horizontally. Find the velocity with which v with which the rifle has a muzzle velocity. Find the velocity v with which the canoe will move after the shot, and the rifle has a muzzle velocity 660 meters per second, and weight of the bullet is 0.28 newtons. Once again, I am repeating the problem. A 667.5 man sits in a canoe Man sits in a canoe and fires a rifle. The bullet is moving. The weight of a man is this one. This is the weight of canoe and this is the weight of bullet. There are three things here. Okay. Velocity of that muzzle velocity is 660. Muzzle velocity of a rifle, this velocity. This is velocity V. U velocity. So now what we have to do, first you take these two as one system. Now according to coefficient of the conservation of momentum, W3U. This is W3 bullet weight and this is W1 and this is W2. Okay. According to conservation of momentum, W3U, this mass final, this is one system. Because of firing a bullet, these two systems will gain some momentum. So that's why I'm moving at the common velocity. When it's firing here, this is moving in this direction together. That is what W1 plus W2 into V and this is W3 into U. Okay. The common velocity can be obtained by W3 into U by W1 plus W2. W3 is this point 28 newtons. Velocity is 660 V. And W1 by V is unknown. U is 660 and W1 plus W2. These two weights. Okay. If we can substitute this, see this is how we will obtain the expression. This expression can be represented as V is equal to the velocity. This is the common velocity we got of boat and man. Now on a wooden block of weight, another problem, a wooden block of weight 22.25 newtons is rest on a smooth horizontal surface a wooden block of weight 20 point rest on a smooth horizontal surface. A bullet weighing 0.14 Newton is shot horizontally into the side of the block. If the block attains a velocity of 3 meters per second, what is the nozzle velocity? Okay. The given data is weight of the wooden block is given, weight of the bullet is given, and velocity of the block is given. Initially the block is at in a condition such that after hitting both are moving together, W1 plus W2 into cos, whereas W1 is initially at rest, wooden block. The initial velocity is 0, that momentum is 0. W2 fires a velocity W2 into U, and Y final velocity is given, together moving 3, V is given, U is asking, that's all. This is what the another simple example we can solve. See, now let us consider the dynamic equation, motion using angular momentum rotation in a collision of bodies. Angular momentum and collision cases, where we come across. in general. What are the different applications and some work energy principles. See, this is when you are rotating a body in two conditions. If we can see, when you are in the morning gym or aerobics, etc. This is the case where, because angular momentum is I omega, linear momentum is mv. Here the I is very, very large, omega is small. Here I is very, very small, the area or volume of it, and omega is very, very large. So this is what is we are calling as the best example of conservation of momentum. Conservation of momentum. Okay. This is what we are calling as the conservation of momentum equations. Now the angular momentum is, with this as origin, I am taking a moment because it is a moment, rotation body, momentum in moment it takes place. That is generally represented with H. L is represented with L. Now angular momentum is standard form represented with H, Hz or Ho. Dependent. This is the Z axis and it is O. The vector notation Hz from the origin, either O or Z, Hz or Ho. This is a scalar notation, force into displacement. A vector notation is R. That is X component, Y component, Z component to F. F is also X component, Y component, Z. Both you take a cross product. That is 3 by 3 matrix you will get. The determinant can be determined as the momentum. Okay. So this is how we will consider the momentum. Now angular momentum is, if you can represent here, I is equal to R cross linear momentum. If linear momentum is PMB, this is linear momentum, multiply with R vector. R cross in both are perpendicular. R is perpendicular to R cross P. P is nothing but, now P substitute here, M into cross V. Then M into, these two are perpendicular, R and V. That is a cross product. Where velocity is R omega and linear momentum is can be V substitute as R omega. M into R, you take outside. M into R cross omega. Outside one R is there, this MR square, that is the moment of inertia omega. See, that's what I omega. See, this is what is as per right hand thumb rule. We can try to represent what is the force and what is the angular velocity direction, etc. This equation what we call as the impulse and momentum. So this is what I have given. Linear momentum mv, angular momentum I omega. The units are given and the definitions are explained here. The linear momentum and the angular momentum. Suppose if you can expand, a little bit blurry there. The linear momentum is product of a system's mass into velocity. Angular momentum is I omega. Equation is this. Apply the object direct path and the angular path, and momentum changing takes place. This is how we generally will try to represent. Now see the work energy principle. The work energy, before got the a flywheel weight like half mv square or half I omega square. Simple kinematic analysis with how to calculate the mk square, mr square, etc. A flywheel like a disc weighing 550 kilonewtons and having a radius of gyration 1 meter, losses its speed from 400 to the example losses a flywheel weighing 50 kilonewtons and having a radius of gyration. It loses speed from 400 rpm to 28 rpm in 2 minutes. The energy gained by the flywheel is gradually releasing. That is what it losses from 400 speed to 280 speed in 2 minutes. Calculate the retarding torque, change in kinetic energy during the period, and change in angular momentum. All the three conditions we can obtain: torque, change in kinetic energy, and change in angular momentum when the body in a rotation. Okay, we'll consider and see that omega is equal to omega naught plus alpha t. Depend upon the data, omega final velocity is given 100 rpm, 400 rpm. This one, initial velocity is given, final initial velocity is from 400 to 280, reducing. Initial, final, time is 2 minutes. 2 minutes. Omega is equal to 2 pi n by 60, n is given. And final angular velocity is equal to initial angle plus alpha t. Alpha is equal to omega minus omega naught by t. Okay, minus 1.0 radians per second square. The weight of the flywheel is 50,000 newtons. Mass is weight by force by this we can represent. The radius of gyration is mk square. M into k. The radius of gyration is given. And having a radius of gyration 1 meters. Okay. Find 0.1 square. 1 square is 1. This is what is the mass moment of inertia. Now torque I alpha. I is determined, alpha is determined. Okay. I mk square, I is known, alpha is known. With two parameters. First obtain the torque, then change in kinetic energy. The final kinetic energy minus initial kinetic energy. Okay. Half I is known, omega final square minus omega initial. 400 rpm to 300 rpm. So this is what is the kinetic energy, half I omega square. Change in angular momentum. I omega naught minus I omega. Final angular momentum minus initial angle. See, like this, when the body in a rotation, you can calculate the kinetic energy and the other expressions. Okay. Now consider the three motions in a body, a combination, translation and rotation. Kinetic energy can generate half mv square, half mv square, and translation and half I omega square. Similarly, angular momentum, linear momentum into perpendicular. This is the linear momentum into perpendicular distance. But here one point is, the mass is concentrated with the distance or a translation component of rigid body experiencing generally plane motion. When the mass is distributed around the pivot joint not concentrated at certain distance or rotational component of rigid body experiencing a general. See, the combination of this plus this, translation plus rotation, we can consider the plane motion. See, that is what the translation is having 1 degree of freedom, or a rotation is having 1 degree. Our translation, if it is a curvilinear translation, we have the 2 degree of freedom. Okay. So this is how generally we will consider the combination of translation and rotation. Now let us see. The kinetic energy can be represented when the ball is hitting the spring. There is a spring, it is translation. When the ball is hitting the kinetic energy of mv square, because it is traveling with some velocity, this is 0, the impulse. Where the time period can be get, we know frequency 1 by 2 pi of k by m. From that, the time can be at time t. I can substitute. Then F average is equal to, after mathematical simplification, we get this is the value. Or if there is a spring, the energy lost by this weight is equal to energy gained by the spring. Like in the elastic region, even if you remove the load, it regain its original shape. That's why if you draw expression force versus displacement or stress versus strain, we'll get the strain energy stored in the system. Or if force versus distance, of F into delta, the area of the triangle, F is equal to Kx. That's why of Kx square. Okay, of mv square is equal to of Kx square. The energy lost by the ball gained, the energy gained by the spring. If you can equate these two, it will be of mv square is equal to of Kx square. Okay, so now if we can further simplify by substituting this, we can get the total. Here consider bullet and baseball. Find out the energy and momentum. If the bullet is a mass and velocity given, let us assume the data is given. Baseball given. For bullet of mv square, of mv square. For the baseball of mv square, of mv square. Now see the angular momentum. Then again mass into linear momentum, mass into velocity. Velocity square and velocity, there is no here, that's all. Mass into half I mass mv square and mv. Baseball. Like that we can determine the. Now as for right hand turn, this is the direct and rotation is the rotation. Both that's why cross one, the cross one, tie cross omega. Here the angular momentum, linear momentum is m cross m is acting dot. Cross part is scalar and it is mv, mass into velocity. When it is in a plane formed by r and f, we can consider. See the person, let us assume a disk. A person is running on the disk. Or with reference to this horse rider along the ground is moving. And these all are the best example of the angular momentum. See, today we have considered some of these aspects of momentum, linear momentum. Now let us see today basically we have concentrated on momentum, conservation of momentum, the moment impulse principle, conservation of momentum, and collisions. These are the three concepts and a little bit the principle of work and energy principle. But there are other concepts, work and energy and more dynamic plane motion. We are going to discuss one more class in the next class. But today we mainly concentrated little bit introduction what we have done in the earlier D'Alembert's principle and Newton's second law form. Now when you are moving that equation with the moment impulse, here when the distance are given, you have to see that the work and energy can be used. If the velocities are given, you can use the moment impulse. If acceleration is given, you can use the moment, that is the Newton's second law and D'Alembert's principle. So this is how we will try to consider the problems. Or in other words, if you take F is equal to ma, force, mass, the space-time relationship, acceleration and time. If you see the momentum impulse, F is there, T is there, mass is there, but there is no acceleration. We are using a velocity. If we can use the work energy, force into displacement is equal to half m square. Kinetic energy is equal to potential. The work energy is equal to F into dx. The kinetic energy is half m square. That is, m is there, v is there, but force into distance. Force is there, the distance is the parameter, new parameter which we are introducing. See, this is how we will consider the problems for the today lecture. And the tomorrow we will concentrate on work energy principle, how this can be applied for different other cases. That also we'll try to discuss. Today, the little bit concepts are given like half k, half m square, like a spring energy half kx square, energy stored in the spring. Or sometimes, depend upon the system, we can consider the expressions, how to consider the energy. But here today only the concept of what is the difference between when the body in a translation, when the body in a rotation. If you combine, you will get a plane motion. That's why the work energy in plane motion, because combination of translation and rotation, that case when we are discussing. Tomorrow I will give the pure concept of work energy principle. Okay. See, tomorrow we will try to discuss those concepts. So today mainly concentrate what is the impulse momentum, how it can be represented in the translation degree of freedom, rotational degree of freedom. Then collision. In the collision case, there is one parameter we are cutting called coefficient of restitution. That can be, E can be vary in between 0 to 1, whereas in elastic, plastic or semi-plastic, etc. cases, how to solve such problem, that is also we have discussed a little bit. And conservation of momentum. Conservation of momentum for translation degree of freedom, conservation of momentum for the rotational degree of freedom. What is the difference? See, these concepts also we have discussed. With this, we'll stop today class. But my dear students, you are not asking any much of questions. Please ask questions through Google Forms. It is a wonderful opportunity created by the government of Andhra Pradesh through APSI, Andhra Pradesh State Council of Higher Education, through the universities like JNT Anantapur, Maine, then JNT Kakinada, and Yoga University, and from our university I am also participating. And in collaboration with these universities, this program is conducting. Please utilize this opportunity. Send your Google Forms. And if any doubts, clarifications are there, we will try to clarify your doubts. And today also one or two hiccups like network problems are there. Please bear with that. But most of the time is okay, but few minutes, like 3-4 minutes starting, there is a problem. Once again, have a nice day. Best of luck. But please send your queries through Google Forms. Thank you very much for your patient listening and hearing. If you have any doubts, please don't hesitate to contact. Don't hesitate to send your Google Forms. Thank you very much for this wonderful opportunity again to interact with you. Thank you, one and all.